All right, hey everybody. So we're going to be talking about infinite geometric series right now, which seems kind of like a strange idea because if you think about a geometric sequence, right, series means we're adding terms together, same like arithmetic series. And so a geometric series, we already know the formula for a geometric series. We had two of them. It's u1 times r to the n minus 1 over r minus 1. Whoops. Or the alternate method was u1 times 1 minus r to the n over 1 minus r. And we kind of used that if r was less than 1, and we used here if r was greater than 1. And having an infinite number of things that you add together seems strange. Because if you think about a geometric series, so for example, let's say you have 3, 6, 12, 24, 48, right? Et cetera, et cetera. So this is a geometric sequence with first term 3 and common ratio 2, right? Because they're doubling things every time. And if you added these together, right, and you added them together for infinity, like they're getting bigger. So clearly that's going to, we use the word diverge. It's not going to add to anything. But the weird thing is, if the terms are getting smaller, so for example, let's say I had something like, let's do something like, I don't know, 81, 27, 9, 3, 1, 1/3, 1/9, etc., etc. If you are getting smaller, what happens is the terms eventually get so small that they don't add enough to go over a certain value. This is a calculus idea that we call limits. There's a limit on the sum, right? So even though we start big, if you add these together and you keep adding off all the way to infinity, it will never go above a certain number. And we're going to develop that formula today. And the way that we usually do this is using a geometric representation of a geometric series. So let's take a look at this. So here we have a rectangle that is 2 centimeters by 1 centimeter. And they want us to cut the box in half, and we're going to shade half of it. So we're going to cut the box in half like this. So the area of each side would be 1, right? Because the area of the entire box is 2. So if I shade in this area right here, that has an area of 1. Let's use a different color for that. We'll use red maybe. Well, maybe. There we go. So if we put a 1 right there, let's make it a little bit thicker too. So the area of that guy is 1. And now if we do this again, so if I divide this guy in half, so the area of the right side is 1. So if I divide it in half, this area is going to be 1/2. So this shaded area right here is going to be 1/2. 1/2. And so then the white area has an area of 1/2. If I cut that in half, the area here is going to be 1/4, right? And it doesn't matter which side you shade every time you do that, right? But if I do that again, so the white area right now has an area of 1/4. I'm going to shade it in half. So the area right here is 1/8, right? 1/8. And so you can see every time I shade, it's half of the previous term, right? So let's say I wanted to add all the shaded pieces together. So first I want us to write a geometric series that represents this problem. So that geometric series, let's use the red for that because that's what we're adding together. So that would be a 1. So we're trying to find here the shaded area. So the shaded area would be equal to 1 plus 1/2 plus 1/4 plus 1/8. Then the next one, if we do this again, right, this guy right here would be 1/16th, and then 1/32nd, and then 1/64th. So let's write those in because I think it's important to see how this is working. So 1/16th, 1/32nd, 1/64th, 1/128th, right? And this goes forever. And basically what we have here is we have a geometric series where the first term is 1, and the common ratio is 1/2 raised to the n minus 1, right? And we're adding that forever. But the weird thing is, notice that no matter how many times we do this, will you ever break out of the box? No, right? You can't ever break out of the box, even though we're adding an infinite number of things together, right? An infinite number of things. We will never, ever, ever pass the total area of the box, which is 2. And you can see, if you start doing what are called partial sums here, 1 plus 1, so we're writing down s's here, right? So S1 is 1, right? The sum of the first term is 1. S2 is 1.5. I'm going to write that as 1.5. S3, if we add a quarter now, is 1.75. S4, so 1/8 is 0.125. So S4 would be, let's see, 1.875. S5, so if I get over here to 1/16, I'm going to have to do that in my calculator. So I have 1.875 plus 1/16. That gives me 1.9375. Let's go up for one more. So S6 is going to be, if I add 1/32 to that, 1/32, sorry, you can't see my calculator, I get 1.96875. And intuitively, I just need you to understand, right, that no matter how long we do this, right, in this corner, there will always be a little white piece. But if you add forever and ever and ever, the way we talk about this in calculus is it's called a limit, right? And the way we write it is, you don't have to know this yet, we'll learn it more later in the year, but the limit as n approaches infinity of the sum from k equals 1 to n of 1 times 1/2 to the n minus 1. We say it is equal to, or k minus 1, excuse me, because we're in sigma notation here. So if you add this together forever and ever and ever, that limit is equal to 2. Right? We will never pass 2. And so we say that the sum of the infinite geometric series is indeed 2, and that's what they're asking here. What is the sum of the infinite geometric series? The answer to that question is 2. So we have the part A here is this geometric series that represents the shaded area, and the answer to part B is 2. So there's actually a way you can calculate this, and it's kind of cool the way it works. I've got a blank page down here to show it. So our sum formula, if r is less than 1, right? Because we already said if r is greater than 1, we're hosed, right? Hosed meaning it's not going to work, because we saw that up at the top here. If you're getting bigger, when you add things together, there's no way it's ever going to reach a limit, right? Because every term is bigger than the last. If you keep adding them together, it's going to increase, we say, without bound. We're using a lot of calculus terms today. There is no boundary level, right? So if r is greater than 1, we're screwed. And if r is greater than 1, we know we use the term Sn equals u1 times r to the n minus 1 over r minus 1. But if r is less than 1, it turns out actually this always converges. It always has a limit. And we use the formula u1 times 1 minus r to the n divided by 1 minus r. And the interesting thing is, as n approaches infinity, so as n gets bigger and bigger and bigger, what happens to r to the n? Maybe you've thought about this before, maybe you've talked about it in a prior math class, but so r we know is less than 1. So we're not talking about negative numbers here, we're only talking about positive numbers. So really it'd probably be more accurate to say that r is between 0 and 1. Right? R is between 0 and 1. As n approaches infinity, so let's say, think about r being, I don't know, something like, we had 1/2 before. Let's say r is 3/4. Right? If you start doing r to bigger and bigger powers, so for example, 3/4 squared would be 9/16. 3/4 cubed would be, 27/64. If you do these on your calculator, even if you just have an intuition here, this is 0.75. 9/16 is less than 3/4, right? Because 3/4 would be 12/16. And it's not 12/16, it's less. 27/64 is even less than 9/16, because 16 times 4 is 64, and 9 times 4 is 36. So we're getting smaller. We're getting smaller and smaller and smaller. And if you do 3/4 to a really big number, 3/4 to like the, I don't know, 75th, let's say. Let's do that in the calculator. 3/4 raised to the 75th. It gives me 4.26 times 10 to the negative 10th. 4.26 e negative 10. So that is 0.1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, 426. And this will happen with any number between 0 and 1. If the closer it is to 1, the higher the power you'll have to use to get it really small. But the point I'm trying to make is that this Rn, we say it tends to 0. R to the n ends up being 0 if n gets really huge, because it gets so small, it's insignificant. We're talking about going to infinity with n. So it's getting so, r to the n is getting so small that it doesn't even contribute to this sum anymore. So what we write, come down here, is S infinity if we think that Rn goes to 0, this turns just into U1 times 1 minus 0 over 1 minus R. And that is U1 times 1, which is just U1 over 1 minus R. And that is the formula for S infinity. You take your first term, you divide by 1 minus R. It's like the simplest formula ever. And it's so cool that it works out. And I'm going to show you that it worked with our rectangle up above. So I'm going to write it in the box here, the magic, like the sacred box, which you guys already have. So it's the first term. And really this should say S infinity. I don't know why it says Sn. It should say S infinity. U1 over 1 minus R. That is the formula for the sum of an infinite geometric series. And let's check out, see if it works out with our box up here. So U1 is 1, R is 1/2, so it should be S infinity is equal to 1 over 1 minus 1/2, which is 1 over 1/2, which is 1 times 2 over 1, which is 2. Right? So anytime you have an infinite geometric series, all you have to do is U1 over 1 minus R, and you're done. Because that whole 1 minus R to the n piece just changes to a 1, because the R to the n tends to 0. So super simple problem here. If you want to try it yourself, feel free. All you have to do is figure out what is U1, what is R, and then put it into the formula. All right, if you pause the video and give it a try, or if you didn't, let's go through how to do that. So U1 is 2, and R, you could get it by dividing, right? This one, it's pretty easy to see that R is 1/5. Sometimes it's hard to see in a geometric series what it is, but you can always take the second term and divide by the first. Excuse me, and that'll also help you see if it's geometric, if it's arithmetic, or if it's neither, because you should have the same thing every time. Here it's pretty clear that we're multiplying by 1/5 every time, but if you wanted to, you could do 2/5 divided by 2, which is the same as 2/5 times 1/2. The 2's cancel, and we get 1/5 for our R. Right, so now our S infinity. So if you add this together forever and ever and ever, I don't know why they have an n there. That should be an n minus 1, right? Because the first term is 2, not 2/5, but I'm going to let it go. Right, so S infinity is going to be 2 over 1 minus 1/5, which is 2 over 4/5, which is 2 times 5/4, which is 10/4, or 5/2, or 2.5. Interesting. So 2/5 is 0.4. So if you write the sums underneath, it's 2, then it's 2.4. I have no idea what 2/25 is, right? But it's tiny, and tiny enough that even already the rest of these terms will not even add up to 0.1 because they're so small, right? 2/25, let's actually see what it is. 2 divided by 25 is 0.08. So this would be 2.48, right? Already we're at 2.48, and the sum, if you keep adding forever and ever and ever, will never go above 2.5. So we say that limit, the top value, the value of the infinite sum, is 2.5. It's kind of cool. All right, let's try a ball bouncing problem down here. They love ball bouncing problems in IB, which is why this one is here. You drop a ball from 1.5 meters on a flat surface. So you're dropping the ball down like this. And it's going to bounce. It's not going to bounce all the way up, though. It's only going to bounce to 80% of its height. So 80% of 1.5, if you multiply by 0.8, is 1.2. And then it's going to bounce to 80% of its height again, and then 80% of its height again, and 80% of its height again. It's going to do this forever, right? And we all know balls eventually stop bouncing, but for this example, we're going to say it's going to bounce to 80% of its height forever, okay? So what do we got going on here? U1 is 1.5, for sure. It gets a little complicated, though, because it bounces, it goes down and it goes up. The first time it only goes down. The second time it goes up and down, and it does that every time forever. That's going to come important. It's going to become in handy for part B. So the first question is, how many bounces before the ball does not rebound over a height of 1 meter? Two ways you can do this. First of all, we're already at 1.2, so it's not going to be very many. If you do 1.2 times 0.8, let me do that in my calculator here. 1.2 times 0.8 gives me 0.96. Already, we have our answer. This is 0.96. So it looks like it bounced once, twice. So A, after the second bounce, it doesn't rebound to over 1 meter. You also could have done that by solving the equation. You could have done 1 equals our first bounce, or our first drop is 1.5. So really what I'm trying to do, if I'm only looking at the drops, I'm trying to figure out when the first drop is less than 1. So if I do 1 equals 1.5 times 0.8 to the n minus 1, And you can divide by 1.5, so you're going to get 0.6 forever, 667, equal to 0.8 to the n minus 1. You can use log base 0.8, or you could graph of 0.667 equal to n minus 1. You get 1.8-ish is equal to n minus 1, and so 2.8 is n. So what this means is it would take just a little over 2 bounces to be able to get to the point where basically the third bounce will be less than 1, right? The second bounce, you're still okay. But the third bounce, it's not going to get high enough, right? So after the second bounce, it doesn't rebound to over 1 meter. There you go. Okay, let me just check my work there. I did that work in the calculator earlier, but I'm pretty sure that's what we got. Yep. Right, so after the second bounce, it doesn't rebound over 1 meter. So now for B, they say find the total distance the ball travels up and down. So the tricky thing here is you have to do the downs kind of as one series and the ups as another. There's another way you could do this. You could just kind of ignore the first one, and you could do just start at 1.2, and you could say it's 1.2, then 0.96, et cetera, and then you could double it and add 1.5. Let's actually do it both ways. The first way I'm going to do it is I'm going to do the downs, and I'm also going to do the up. So here the down is going to start at 1.5, and then it's going to be 1.2, 0.96, et cetera, all the way off to infinity. And the ups only start at 1.2, and then 0.96, et cetera, right? So the downs, we're going to have S infinity is going to be 1.5 over 1 minus 0.8. And for the ups, S infinity is going to be 1.2 over 1 minus 0.8. And then we're just going to add them together. So the downs, let's see, 1.5, get back to the end here, 1.5 over brackets 1 minus 0.8, or just 0.2. I get 7.5 meters total going downwards. And the ups, we got 1.2 times 1 minus 0.8. And that is, uh-oh, I missed a division sign. Insert division sign. There we go. 6. So all together, up and down, 13.5 meters. Now, I said there's another way you could do it. So where'd my extra page go? Here we go. So let's say instead you wanted to think about it. So we have 1.5, then we have 1.2, then we have 0.96, and it's going to keep doing this forever, right? So I'm going to ignore the first one, and I'm just going to start at 1.2. So S infinity is going to be 1.2 over 1 minus 0.8, which we know is 6. And then I'm going to multiply that by 2, because that'll give me the up and the down for 1.2, the up and the down for 0.96, maybe the up and down for all of them. So multiply that by 2 gives me 12. And then what do I have to add? I have to add the first one. So plus 1.5 gives me 13.5 again, meters. Same thing we had here. There you go. Ball bounce problems, classic IB problems. Love them. Great question because it makes you think about that first drop. And you can't just do infinite sum from the first drop and double it, because that would assume that it started from the ground, right? But that didn't happen. You could do that, and then you could subtract the 1.5 as well. That would also work. Okay, last one on the page here. Meteorologist models the height of a hot air balloon launched from the ground. Okay, so hot air balloon launches from the ground. The model assumes the balloon travels vertically upwards and vertically straight up. Travels 450 meters in the first minute. So there's 450 meters in the first minute. Due to the decrease in temperature as the balloon rises, the balloon will continually slow down. The model suggests that each minute the balloon will travel only 82% of the distance traveled in the previous minute. So the second minute, it's not going to go quite as far, right? And then even shorter, and then even shorter, and then even shorter, and even shorter. This is going to happen forever. So let's see what 82% of 450 is. 0.82 times 450. I get 369. So 369 here times 0.82. Is probably the last one that I'll do. Gives me 302.58. So it's rising, but less each time. Kind of like the bouncing ball, right? It's a little bit less each time. So, first question. Find how high the balloon will travel in the first 10 minutes after it is launched. So they're here asking me for S10. Right, because the first minute's 450, second 369. They want to know how high is it after 10 minutes. So that will be 450 plus 369 plus 302.58, et cetera, up till the 10th one. I don't know what the 10th one is, but I don't have to, right? Because we know this is equal to, it's going to be u1 times, let's see, it's 0.82, so I'm going to do 1 minus r to the 10th divided by 1 minus r. So this is going to be 450 times 1 minus 0.82 raised to the 10th divided by 1 minus 0.82. And that gives me 450 times 1 minus 0.82 raised to the 10th power divided by 1 minus 0.82, which is, of course, 0.18. That gives me 2,156.3799. We haven't talked a lot about this yet, but if we round that to 3 sig figs, that's 2160. They will take this. They'll take anything that would round correctly to 3 sig figs, or you can just write it in 3 sig figs. That's totally fine. That's meters, I believe. Cool. All right. For B, the balloon is required to reach a height of at least 2,520 meters. Determine whether it will reach this height. Notice they don't say in a certain number of minutes. This is ever. Will it ever reach that height, right? And we just talked about this. There is some limit, right? That's the whole idea of our infinite sum. There is some limit that we will never reach, right? And we say that is the infinite sum. That's how we define the infinite sum. But if it's less than 2,520 meters, then it's not going to get there. So let's see. So S infinity here is going to be our first term, 450. That's a bad 5. 450 over 1 minus 0.82. So 450 over 0.18. Oh, it gets so close. 2,500 meters is the max height. So it misses it by 20 meters. That's crazy. So no, won't make it. All right. For C, once again, we've been talking about this a little bit. A limitation for the model. Lots of things we could say, right? One is they don't talk about the horizontal motion at all, like wind. If there's wind that's blowing it left and right, maybe it won't entirely just be going upwards. One is that I think the balloon is going to shrink as it rises. So they're not talking at all about the size of balloon. As you get higher, like I don't think that the cooling will be even. So that could be something you could mention. The cooling isn't even. Maybe you could argue a bird might pop the balloon. I don't know. You can really say whatever you want to these. As long as there's any kind of a valid thing that you give, it doesn't matter. And that's actually what they say down here. So check it out. We got the first one right. We got the second one right. And just so you know, M stands for method. So this is 1 mark for the method. So just recognizing that it's geometric. The brackets here mean it's not a necessary step. You can get it without directly writing it, but as long as you get to the final answer, you'll get that kind of intermediate mark as well. A stands for answer. So method again here. R stands for reasoning. Yeah, and they sometimes write some notes here. Sometimes mark schemes are useful. Sometimes they're just like you can't really understand. It's kind of like the answers in the back of the book, but sometimes they're useful to read. So what do they say here? Horizontal, we talked about. Rate of cooling not linear, so we talked about that. The cooling won't be like as smooth. Balloon is a point mass. That is a physics thing saying that the size is not considered. They're considering it to be exactly in 1 point. Weather, unlikely to be consistent, so talked about wind. Discrete has been used. Continuous one may be greater accuracy. So what that means is they're only considering every 1 minute. So 1 minute, 2 minutes, 3 minutes, 4 minutes. They don't, like the model might not work for, 10.7 minutes or pi minutes or something like that. But once again, any sensible answer is taken. So as long as you write something, usually it's okay. Hopefully this made some sense for infinite geometric series. The formula, biggest thing, right? As long as you can use that, you're going to be in good shape. All right, good luck. There's one more thing that we're going to talk about in kind of this section of the unit, which is compound interest. So make sure you check out that video as well. Good luck.